Thank you. Hello, everyone. As Holger said, I will be talking about the unification of the batch and the stream processing APIs on Apache Flink. So that's the title up there. I'm a software engineer at Viverica who pay me to work on Apache Flink in the open source and to do talks and other interesting things. And I'm also a member of the Apache Flink Management Committee and the Apache Beam Project Management Committee. And if you feel the need to reach out to me, you can reach me at Alyosha on Twitter. So before I start, what I'm presenting is the work of many members of the Apache Flink community. That's people that I work with at Viverica, but also people that work at other companies and that we work with on the open source project. So, what are we actually trying to solve? The current state is, or the current state in the APIs, is that we have a DataSet API, which is used for batch processing. We have a DataStream API, which is used for stream processing. And we have a table API, which includes SQL, which is used for relational style queries. And this API is actually can be used for both batch and stream processing. So I'm going to put that aside for today and mainly focus on the DataSet and the DataStream APIs, which are the programmatic APIs, if you will, of Flink. What are actually the differences between the DataSet and the DataStream API? So one of them calls the collection that you work with DataSet, the other one calls it DataStream. That's an obvious difference. One DataSet has group by, DataStream calls the same thing key by. But other than that, there's a lot of similarities. All of them have map, filter, flat map. They have join and co-group and these kinds of operations. But additionally, what separates the DataStream API from the DataSet API is that the DataStream API has first-class support for working with event time. So that means that the records that you are processing, they can have a timestamp, and that the streaming job that you write with the DataStream API takes account of that timestamp. So when you, for example, have sensors that create data you want to aggregate, say, hourly or weekly, you want that time to play a role. And that's what we call event time. That's what made Flink very interesting to a lot of people. So we have that. With that comes, as I mentioned, first-class support for windowing, first-class support for event time timers, where you can express complicated business logic, where you want to wait for certain things to happen in event time and then do certain processing steps. And as one of the basic building blocks for working with event time in the DataStream API, we have watermarks, which are the thing that we use to keep track of the time in a stream. So that's required for working with event time because we have to have a way of keeping track of time. But it's also a bit of a difficult thing to work with because you then have things like late data that you need to consider and trade-offs between completeness and latency and other things. We'll go into detail about this later. So now that we know about the main differences, what are we actually trying to achieve with our work, or what did we try to achieve? We want to change Flink such that we only have one API that you can use for both batch and stream processing. This, in hindsight, it seems somewhat obvious because if you look at the DataSet and the DataStream API, they are so similar that you wonder why are there even two APIs in the first place. And a data stream in the DataStream API can be bounded, and you can write bounded programs using the DataStream API. Some of you have probably done that in tests or also other cases. So that's a very obvious thing that would also reduce the cognitive load for users of Flink. If you only have one API that you need to learn instead of two, that's quite a bit more simple. And if we only have that one API, then that makes it easy to reuse the same job for real-time processing and then use that same job to also process historical data with the same business logic, with the same behavior, the same semantics and everything. So we want to have semantics for these jobs in the DataStream API that make sense across both batch and stream processing. And as a last thing that maybe users of Flink don't consider that much, but it's important that we have a unified API for connectors, so things that connect to external systems such as S3 or Pulsar or Kafka, say. And if we have one API and we have connectors that work well with that API for both batch and stream processing, we make it a lot simpler to use the external system that you want. So But now I use these terms like batch processing and stream processing, bounded streams, unbounded streams. So I should quickly clarify what we mean by that, because I will use that in the following a couple of times. So a stream is essentially, you can think about it as an infinite stream of data. In real world, it has a beginning because we're not in an really infinite universe potentially, but it normally doesn't have an end. And data just keeps coming in, and you just keep processing things when you're processing an unbounded stream of data. A bounded subset of such an unbounded stream has a definite beginning and an end. So you can, for example, collect the data for 1 week from some sensors, which are an unbounded stream, these events from the sensors. But if you then say you take a data set for only a week, that would be a bounded subset of such a stream. So that's about streams that are bounded and unbounded. And we can extend that concept to jobs. So a job in the DataStream API, say, has a couple of sources, then it has a couple of operators, and then there's one or more things that write data to an external system. And if all the sources in a job are bounded, then the job is also bounded, because we know there is an end to the data, so at some point the job will finish processing. If, however, at least one source is unbounded, that means the whole job will be unbounded, meaning there will always be coming in more data, so the job will never finish. It will just sit there and keep processing more data. So if any source is unbounded, the job is also unbounded. And that leaves me with the terms batch and stream processor, or batch and stream processing. So here the way I use these terms is that a stream processor is a thing that can both work well with unbounded streams, so it can do unbounded execution, but because bounded streams are basically a subset of an unbounded stream, and you can just have a stream processor that shuts down at some point, a stream processor can also be used for bounded execution. A batch processor, on the other hand, is a system that can only be used for bounded execution and not for unbounded execution. So that's how I use these terms in the presentation. So by now, if you're paying attention, you might be wondering, I can use the DataStream API to write bounded jobs, right? You probably have done that in examples, and you have run examples in the IDE with the DataStream API that start and finish, so they are bounded, right? However, if you use the DataStream in such a way for bounded programs, they don't necessarily execute as efficiently as they could. If you use the DataSet API, for example, there will be different runtime algorithms and data structures used underneath that are more efficient than what we can do in the DataStream API. I will go into that a bit later, but for now, let's see what it actually means. What is efficient or what is inefficient? So here I have a couple of definitions from the internet. So efficiency means achieving maximum productivity with minimum wasted effort or expense. Or it means working or operating in a way that gets the results you want without any waste. And with this in mind, I'm saying here that there is two kinds of inefficiencies. There is inefficiencies that the user has to worry about, so you as the user of the DataStream API, for example, where there are some things in the DataStream API that are not necessary for bounded programs. So if, for example, watermarks, which are used for keeping track of time, but which are also difficult to work with because you have to consider late data and completeness and all those things, you have processing time, which is tricky to work with. These are inefficiencies that you, as a user who just wants to use the DataStream API for bounded processing, shouldn't be or shouldn't have to worry about. So these are inefficiencies. I call them inefficiencies in the job semantics, generally in the semantics of the API. And the other set of inefficiencies is inefficiencies in job execution. So there is different strategies that you can use when you know that the incoming data is bounded or unbounded. And when you use, say, a stream processing system to process bounded data, then you will leave some performance on the table because you're not using algorithms or data structures that are as efficient as they could be. So we'll also go into that a bit later in the talk. Here, I just want to quickly reiterate some of these inefficiencies in job semantics. So I mentioned already they mostly come from working with event time, where you have watermarks and then you need to know, can I have late data? What should happen when I have that late data? Do I want to basically update the result that I already sent downstream and produce a new result? Or do I want to ignore it? Do I care more about latency? So do I want to have results very fast? Or do I care more about completeness? So I'm willing to wait for a bit, but have more complete results. These are all trade-offs that you need to be aware of when you're using the DataStream API for stream processing. But if you want to use the DataStream API for a bounded job, that's not something you should have to worry about. So with this bit of background knowledge, let me quickly restate our goals. So what we want to do is we want to modernize the semantics or the DataStream API to potentially make sense also for batch execution for bounded programs. 2, we want to add an efficient execution mode underneath the DataStream API so that bounded programs can be executed as efficiently or potentially better than what you could get with the DataSet API or a purpose-built batch processing system. And then the whole thing that started this endeavor, if you will, is that we want to deprecate the DataSet API such that we have one unified API for everything, which will make it easier for the user in the end. And also easier for us as a developer because we don't have to maintain 2 separate sets of APIs. So this section is very short. And there's basically only one thing that we needed to look at in the DataStream API to make it work well for both batch processing and stream processing. And that is, you can probably guess it, it's mostly about time when we're talking about inefficiencies. So we asked, does processing time or ingestion time make sense for batch processing? So to quickly recap, event time processing is when you consider the timestamps that are inherent in the events and you do aggregations based on those timestamps, say. Processing time is when you only look at the time on the machine at the time that it is processing the data. So with processing time, it's a bit easier to work with. You don't have late data, but it's not as accurate as event time can be because, again, it ignores the time in the data. But if you look at the streaming job example, if you process real-time data or near real-time data, processing time is good enough because the position where you're reading that stream or what data you're processing correlates roughly with the time on the machine. So in Java, if you just say system current time millis, you get about the same time that you would get on the sensor that sent that data to you a couple of seconds ago. So there's only a couple of seconds of mismatch between processing time and event time. So it can be okay for streaming jobs, but I still think using processing time is mostly a mistake. So I would always recommend to use event time, but it's there if you want to use it. However, for a batch job, where you have, for example, some data that you have sitting around from sensors from say 3 weeks ago, and you want to do time series analysis, you want to aggregate, say, some temperatures over hourly windows in that data. Now, if you use a batch job for that, and if you use processing time, that would be completely uncorrelated to the time in that data. Because if the batch job checks what is the time, then the time is now. And in the data, you actually have timestamps from 3 weeks ago. So very different. So we said it doesn't really make sense to use processing time with batch processing. So what did we do? We deprecated this setting called stream time characteristic in the DataStream API. So the stream time characteristic is a thing that you set on the stream execution environment. So you set this globally for a job, where you write a job using the DataStream API. And this tells the system what is the main mode of time or the main characteristic of time that we're using, say processing time, event time, or ingestion time. And up until now, the default for this was processing time for historical reasons. But we said now that we want to modernize this, we switch it to event time, and we actually deprecate the setting. Because most people that use the DataStream API for event time processing, they have this boilerplate where they have to say, set stream time characteristic event time. It's just boilerplate. You don't really need it, so we also deprecated that. So if you use the DataStream API for stream processing, that's an important thing to remember. You'll also get a warning that's deprecated, but that's the one thing we had to change really on the DataStream API to make the semantics make sense for both stream processing and batch processing. With that out of the way, we can move on to the interesting part of this work, where we actually introduce batch-style execution on the DataStream API. And the way we're doing this is very simple. There's just a setting that you can set. It's called execution.runtime-mode. And that setting controls how the underlying runtime of the DataStream API will execute the job. And there's 3 settings. There is streaming, which is the classic DataStream execution behavior that you know. There is batch, which is the new execution mode that we're introducing, and I will talk about how that actually works in a bit. And there's automatic, which will look at the sources in your job. And I've talked about this before. If all the sources are bounded, then the job is bounded, and we can choose batch execution mode. But if one of the sources is unbounded, then we have to use streaming mode. And so automatic is the recommended way of running things. But we chose to put streaming as the default for now because we didn't want to surprise users when they update to Flink 1.12 if suddenly their jobs that happen to have bounded sources would switch to this new batch execution mode, because there will be some differences in how it behaves. So it's important to not surprise people. And then you can set the setting in your code, in your DataStream program, or you can set it in the bin Flink run command. You can say execution runtime mode batch or streaming, and pretty straightforward how you use it. There's just this one setting that you set, and then you get different execution behavior. And now I will actually go into what changes when you enable batch mode compared to streaming mode. So let's look at how watermarks work in streaming mode. So watermarks are these elements in a stream that tell us about the progress of time in a stream, because we can't use the wall clock time, as we said, because the data might be from, say, 3 weeks ago, or it might be a 5-minute delay between the sensor and the processing system. So there's this extra element in the stream that Flink inserts, so that come from an external system, that tell us about the progress of time. That's what these watermarks do. But there's problems, as I mentioned before. There's these semantical inefficiencies that I talked about, that you have to consider lateness and completeness latency. So there can be data in your stream that is late, and then you have to handle that, which can be a hassle. So in batch mode, it will behave differently. So in batch mode, there's no infinite stream of data. You don't have to keep track of the time in your data. You have this one batch of data, and you know where it starts, you know where it ends. So logically, the system will have the watermark at -infinity when before processing the data. It will process the data. You might set event time timers, or there might be windows, or any number of things going on. And then once we process that bounded stream, that batch of data, the watermark immediately jumps to +infinity, or in Java terms, it's long min value, long max value. But this way, you never need to worry about late data or anything for batch execution mode. We did a similar thing for processing time in batch mode. So for processing time, we said processing time doesn't really make sense for batch processing, but it might be that you write a program using the DataStream API that uses processing time. So in those cases, you still want that same program that you wrote once to also work in batch execution mode. So what we do there is the same thing that we do for watermark, where we say basically at the beginning, the time is -infinity, and then at the end, it's +infinity. And we also fire any timers that have been set or any processing time windows that happen during that time. So that's the very important changes about how we handle time in batch processing mode. So now let me talk about execution or actual execution in batch mode versus streaming mode. So in streaming mode, an operator or a program, a streaming program, is basically a process that sits there that keeps, if you will, a hash table of, say, counts that it updates. So in this example, we have an operator that counts how many times a word appeared. So it has a hash table where it has the count, and if new data comes in, it goes to the hash table, it does a lookup for every new record that comes in, updates that value, and potentially emits that value downstream. So here we see a couple of foos, and then we always send a new update. So we have foo 43, foo 44, then there's a bar in between. But the stream operator has to be always running. It never stops, because we never know when the input might finish. We can extend that to a whole job, where we have a whole job where all the operators are always running, and there are some that have state in them, so they have a hash table-like thing. I think this is called a state backend, so there can be rocksdb, for example. And it can be quite problematic if the key space is very large, because then these operators, they might be sharded across different machines, but they still have to keep a lot of state in memory to be able to react to the incoming data and to produce new incremental results. And what Flink has to do is we have this thing called checkpointing, which periodically checkpoints the state of all the operators in the topology so that we can restart them in case of failure. And then it's somewhat costly, where if there's a failure, all the operators have to restart, we have to reload the checkpoints, and then we can continue processing. For batch mode, we can be a bit more clever. So what we can do is, say we have a batch counting operator, it knows that the input is bounded, so it can read all that input, say, sort it, and group it by the key, so in this example, by the word. So we would have a group of only foos, a group of only bars, and other words. And then we can do one pass over the data where we just count, for example, how many foos there are, and then send a result downstream with only that count of foos and only one. So you wouldn't have all those incremental updates for the count of foo, but only one update, and same for bar. And this extends to the whole job. So in a batch job where the input is bounded, we can execute these operators one after the other. So we can first, for example, execute this source at one point. So say in one stage, then we execute this other source, then we execute the third operator, and then the fourth operator. And these operators, they can materialize the results between these individual operators such that when there is a failure, we don't need to restart the whole pipeline, but we can, for example, if operator 3 completed successfully and operator 4 fails, we can fall back to the result that operator 3 already produced and just continue from there. So we don't need to do checkpointing for fault tolerance. So it's a different behavior when it comes to execution, because you execute things one by one, and you don't have checkpointing, but you use backtracking for failure recovery. So that's important. There's no checkpointing in batch execution mode, so this means that functions or operators that relied on checkpointing, if they were doing business logic on every snapshot or when they were listening for completed checkpoints, that doesn't work, which is a bit of a complicated thing because it also affects the built-in sinks that Flink has. I'll get to that in a second. But you can still use the state API as before. So you can use a value state and a list state, say, and they will just work. It's just that the mechanism behind it that makes it fault tolerant is different, and it will be executed in a different way, where there's just one pass over all the records of one key so that we can keep very little amount of state while we are processing those groups of keys that we created. So, to summarize the changes that we introduced for this new batch execution mode. So there's no intermediate time processing rule. There's no watermarks that go on as the stream goes on. There's just, we go from minus infinity to plus infinity. And same for processing time. Also, for the execution, we don't do this incremental streaming style execution mode where all the operators are always running and we incrementally update new results. But instead, we have this batch style execution where we can execute operators one by one, where you can have different stages, and where we can use these efficient execution strategies where we do a sorting and a grouping, and then do one pass over the data to do the counting, which also works for existing programs that use the state and time API. So a process function will still work with this. So it's quite interesting. And I encourage you to check out some of the flips I mentioned later to see the details of this. And a very important thing, there's no more checkpointing. So this is definitely something to be aware of when using batch execution mode. These are some of the implementation details, if you're interested, and I definitely encourage you to check them out. So Flip is a Flink improvement proposal. So these are design documents that the community votes on, and they're more coarse-grained, and they basically affect the more long-term planning and evolution of Flink. And there's an umbrella flip where we decided that we wanted to deprecate the DataSet API, and then there's flips for more concrete things, like for the semantics of the DataStream API. There's some more details that I didn't have time to mention here, so I encourage you to check that out. And there's flip 140, which is about this different local strategy of sorting and grouping and doing a one pass, which we can do in batch execution mode. So that's also very interesting. And then there's details like there's a new source API, which works for batch and streaming, a new sync API that doesn't rely on checkpointing, which works for batch and streaming. All of these are very interesting to check out. That brings me to the final section. So we ran a couple of comparisons to see how this batch execution mode compares to streaming execution mode. So when you actually run it, it's very boring. So what I did here in this recording, I'm starting a Flink cluster. I'm running the streaming word count example, and I'm saying I want to run it in runtime mode batch. So I just run that. It's very straightforward. Just say that, it runs, takes a couple of milliseconds because it's just toy data. Then I do the same thing for streaming mode. And it also just runs. It's really not that spectacular. But what's happening under the hood is the interesting thing. So this is just some toy data, but we also tried this with somewhat bigger data. So we had 14 gigabytes of input data. We ran it as a parallelism of 100 operators on machines that had SSDs. And if you paid attention, you can guess which one is the stream processing mode and which one is the batch execution mode, because you can see you have these blue bars which tell you when operators are running. So in the top one, you see that all the operators are running basically all the time. So the top one is the source, and the other one is the aggregation operator. So the source finishes eventually, and shortly after that, the aggregation operator also finishes. And in the bottom graph, you can see that we first process the source, and then we process the aggregation operator. And the scale is a bit misleading here because the bars are basically as long as the job execution time, but the job execution times are different. So for the streaming execution mode with the RocksDB backend, we had 1 minute and 20 seconds roughly, and for batch mode, sorry, I have to read this, this went down to 38 seconds. So that's actually quite the improvement also on this modest data set. But we will do more benchmarks and then do more analyses and publish blog posts about this with more details. So we're almost done. I want to quickly mention some future work, only very briefly. The work that we did now is we introduced this streaming mode, this batch mode, but they only work, separately. You can either execute it in streaming mode or you can execute it in batch mode. You cannot do mixed jobs where you say you have one part of the pipeline which should be executed in batch mode, and then once that is finished, I want to start this other part of the graph that should be executed in streaming mode. So this mixed workloads don't work yet. If there's one unbounded source, the whole thing has to be executed in streaming mode. And another interesting thing that we have been thinking about for a long while is state bootstrapping, where you might want to use a batch job in batch execution mode and create a save point from that and use that save point to bootstrap the state of a stream processing application. So to bootstrap the state from historical data and then switch over to real-time processing data. So we are at the end. So what did we want to do? We want to deprecate the DataSet API eventually. For this, we modernized the DataStream API semantics to make more sense for batch execution. We added a new efficient batch execution mode. And you can now use the one DataStream API for both batch and stream processing, and you should get good behavior when it comes to semantics, so you don't need to worry about watermarks and lateness for batch execution mode, and you get good, efficient execution behavior. And this code is in Flink Master, and it will be released in Flink 1.12 once that is coming around. So feature freeze is in a couple of weeks, so that should be any time now. So thank you. As I said, you can try out this code. You can check out Flink Master, run the examples, or run it on some data that you might have. And I'd be very interested if you have batch processing use case and you want to use the DataStream API with this new execution mode for that. So please reach out. You can reach me at Alyosha on Twitter, or it's also alyosha@apache.org via email. And just follow the Flink website where we might publish a blog post with some more benchmark results and some more in-depth explanations for these different execution modes and this one pass and everything. So I think I have a couple of minutes now for questions if you have any.